All right, hi y'all. Welcome back. We're going to do an example here from concept quiz. Which one are we doing here? Concept quiz 9, and I think Rebecca had a specific request for me, right?
Yeah.
Do you have a sense of which one you want me to do?
I think we could do this one. F.
F. Okay, so we're going to work on letter F. And indeed, Abby, I think you were also having me think about that one, right? Yeah, so let's go ahead and do that. So I guess this is problem letter F. So we want to show that 2x plus 4 over, I guess this is 3x plus 6, is actually identically equal to 2/3. Okay, so let's consider the start of this thing, which is 2x plus 4 over 3x plus 6. Any suggestions on where to start with that?
Factor the biggest factor.
We'll do this thing, same thing kind of we did last time. On the top, is there anything that comes out of both terms? 2. What happens if I pull out a 2?
X plus 2 times x plus 2.
Yeah, so then in this case I would have x plus 2. And then what about,
Well, 3.
yeah, okay, so now I've got a 3 times x plus 2. And that was by factoring, right? So we factored top and the bottom. Okay. So next step there. So let's do a quick recall. We're going to come back to this, and in fact, in the very, very next thing that we do, we're going to spend a lot of time talking about this. So this is a famous property of fractions. If I multiply a fraction a over b by another fraction c over d, what's the claim when I have the product of two fractions?
1.
Yeah, that was really eloquent. So you're telling me if I have a product between, I can actually bring the multiplication both on the...
Now, I was listening. I thought, did what you say not match what you wrote? Okay, because I was listening, and now when I was like, wait, when I look, because I'm just ready to slash out the x plus 2, x plus 2.
Yeah, you're a little fast for me. But we're going to get there. I promise you that we're going to get there. No, that's beautiful. I always say that my students are better dressed, faster, more intelligent, right? You got to remember that I'm like an old man. I always say that I'm like that movie It Follows. Have you seen that one?
No.
Okay, don't watch it. It's scary. But the point is there's something that's really slow that always gets to where it's going. That's me in math, right? So the claim is when I multiply two fractions, what can I do?
Yes, a.
Multiply the things on top. Oh, God. Yeah. Multiply the things on the bottom. So now this is A times C, B, D. And then you remember what I was talking about? Every equation we call a two-way. Yeah, it's a two-way street. So I can actually go both directions. Notice if we start using colors. I should have let you all choose the colors. I'm still getting my workflow systems here. All right, so what do you notice there? How many different fractions are in that one? Yeah, we've got two separate fractions, one orange and one blue, but over here, those two fractions become one. Okay, up here, is this two separate fractions or is it a single fraction? Single fraction, so we start at the end of the street rather at the beginning of the street, and the claim is we can traverse it backwards. What would I do if I traversed backwards?
It's 2 divided by 3. Multiply x plus 2 divided by
Very nicely done, Elisa. Okay, and the claim there is what we've done is we've broken this fraction into two. Why is that special? And you all kind of, Abby kind of already guessed, understood. And so Elisa and so Molly, this fraction right here, what do we know about it? Yeah, so you're telling me there's this very, very famous property of fractions that says,
What's the name of the property?
I don't know, should we give it a name? Maybe we'll give it the Molly property?
Yeah, I'm sure it does a name.
I'm sure it does, yeah. Yeah, I mean, if I really wanted to get real nerdy, I would say it's the equivalence class of rational numbers. That's well beyond the scope of this class.
Yeah, no, it's got a name.
But yeah, so the idea is that if the thing on the top matches identical to the thing on the bottom, that fraction is 1. What's the one condition?
If it's not 0 on the bottom.
Yeah, the bottom can't be 0. So we're going to make a claim that this whole fraction goes to 1. But what was the one condition that we had? The thing on the bottom,
Yeah, okay.
whatever's on the bottom can't be 0. Right? Okay, so I'm running out of room. What does a rookie mathematician do when he is running out of room? Right, and what does a pro mathematician do when she's running out of room?
Hopefully has more paper.
Get it? Yeah, and I always have paper here, right? Okay, so the claim is, what is 2 over 3 times 1? 2 over 3. That is only true when the bottom is not equal to 0, but when would the bottom be equal to 0? What value of x would force the denominator to be 0? X is not -2. How many of you are going to go into the 48 sequence? 48A, 40. Okay, so in this case, you have to be conscious of it. I want you to study that. For the rest of you, don't. If you're not going to go into the 48 sequence, 48A, 48B, the pre-calculus sequence. So if you're going to go on to stats, or maybe this is your last math class, just the fact that you cancel these out is great. In your case, it's going to matter because these will indicate what we call a vertical asymptote. When you get to that place, you're going to rock it, don't worry.
Okay.
Yeah. Okay, so what Abby did, I don't know if I can show your work. Is that okay? So she did this really beautiful thing. I call this pure genius, right? Because she did like 5 steps at once there. So she literally said to herself, like, whatever's on the top cancels out on the bottom. What's that actually mean? So she pulled out those 2 factors. She recognized that the thing on the top and the thing on the bottom equal 1. When I multiply by 1, nothing happens, and I'm done, right? Yeah, so in 1 step of genius, she actually did like 4 or 5 steps of math. Same output, beautiful. Cool. Should we go on to the properties?
So you said x is not negative.
Yeah, so the one claim on that is that, because the funny thing about this, so check this out. We could actually do this on a calculator to confirm this. So this fraction, we're making a claim that that whole fraction is equal to what? 1. But if I were to actually type that fraction in, so let's go to y equals, and we'll go to f1, numerator over denominator. So this will be x plus 2 over x plus 2. So now we're going to look at that fraction at the table. So notice that almost all values of x, let me turn that light off. So what do you see for that fraction about almost every single value of x? What's the value of? Usually 1, except what happens
A notable exception.
at -2? There's an error, right? Yeah. So what ends up happening is this function is indeed equal to 1, except when the denominator is 0. And I think maybe it's worth going into this. This is, I've had many students tell me that this is quite confusing, and I actually remember that this is confusing. So let me see if I can do, which is called, I feel not as old as I used to be, but I'm still figuring this out. I think this is pretty cool though, right? To have full access to what we just did at any time. Yeah.
So I have a question.
Yeah, go ahead, shoot it from the hip.
The number F.
Yeah.
Like, so you know how you have
Yeah.
Can't you also separate them with 3, but be 2 over the third times x over the x times 4?
Oh my God, I love that. Yeah, let's.
That's how I came up with it, and everything's still factored into 2.
Oh, I'm really liking this. So this is actually a really, really beautiful.
And I did not have enough room, so.
Yeah. So what's funny about this though is this right here is really special. This is a really common. We might call it a mistake. I'm going to call it an opportunity for growth. And we're gonna go through this together. You're doing absolutely beautiful. I love this. This is what I would call genius. You're applying the right idea in a different context. Sorry about that, Molly. Let's go back to this. There we go. Okay, so she just did this really beautiful thing that I've seen tens of times. Let's come back to this in just a minute. So we're gonna do a little bit of a review first, and then we're gonna come back to this problem to answer this question.
Okay.
Yeah, so I promise we'll get here, Rebecca. That's a beautiful question. Okay, so what I want to do is just a quick overview of fractions as fractions. All right, what did we call the thing on top again?
Numerator.
Yeah, so we call that a numerator. And what do we call the thing on the bottom? Denominator. I want to do something that I think is kind of rare, which is to analyze the meaning of a fraction. This is where I want to get mad at all English. I generally speak in English, so I can't hate it. But the use of English for fractions is really not helpful. So I kind of want to review the meaning of a fraction. And to do this, I'd like to kind of choose the least difficult, I suppose we might call it, or least painful version of a fraction. So can you give me a kind of a easy fraction with a small numerator and a small denominator? Hopefully the denominator is smaller than the numerator.
1/2.
Okay, so let's look at an example here. Call this example 1. Let's look at 1/2. And this is where I want to get really, really angry with the words 1/2. Because this English is completely useless. It has no meaning. In Japanese, I used to live in Japan, and one of my life dreams is to speak 5. This would be called Nibun no Ichi, and that's a little bit better. What's actually happening with this fraction is we're going to actually start with a whole. And then I would ask you, do you all like chocolate, money, or pizza?
Money.
Oh, I had all three. Since I like chocolate, I'm gonna break that tie. So we're gonna start with a whole chocolate bar. I guess I like money because I can buy chocolate with money. And then pizza just gives me calories. Okay, so this whole thing is what we're gonna call one whole unit. And in this case, I am really salivating when I'm thinking about this as a chocolate bar. Okay, so after I start with a whole, so this would be called, I don't know, like step 1 or something like this. What do we do to that whole? Yeah, we cut the whole into how many equal parts? Yeah. 2 equal sized parts. Right? So this is, we haven't even finished what the fraction actually means. We're literally just constructing the fraction 1/2, and this is why I get really angry at the English language, because the hell does 1/2 mean? Okay, so now I take the thing and I have to get like a ruler out, because Elisa's going to want half the chocolate bar, and if I cut it unequally, she's going to get mad at me, right? At least I would get mad at her if she cut it unequally. Okay, so first I start with a whole, then I cut it into half. How did I know that I was supposed to cut it into 2 pieces? Where did that come from? Yeah. So the reason that I cut it into two pieces, the number of pieces I cut into is stored where? Yeah. Very nicely said. Okay, so we haven't even finished the fraction yet. We're still trying to get to the point of what the hell the fractions is. I'm really trying not to cuss right now because, yeah. Okay, what do we do now? So what does 1/2 mean?
Well, on the top, you're talking about parts of the bar,
Yeah.
parts of the whole.
So then what we do is we take how many of those pieces. So if I look at that fraction, how many of those pieces am I going to take?
One.
Yeah. I take one of these pieces. Okay, so the whole idea was I took one whole chocolate bar, I cut it into two pieces. In this case, the fraction was 1/2. So up on top, that tells me take one of the two pieces that I constructed. So that is what 1/2 means, which is just stupid, right? Like, think about how much is going on in this process of doing 1/2. So I'm having a hard time right now because every time I switch over to full screen mode, the viewer doesn't get actually to see the full screen. So I'm kind of watching along on YouTube to see what they see. Yeah, so I'm not sure what's going on here. One thing that I could try to do is kind of...
Pause.
Is that a little better? Can you see that? The question is, could I make this bigger? Full screen interface, maybe. It's not great, huh? Can you see that?
Were you paused?
I'm not paused right now. I'm still going. Can you see my work there? Yeah. Okay. It's not too small. All right. So let's think about this for a minute. What does it mean, 1/2? So what are the three things that I do when I construct a fraction like that? First thing that I do anytime I'm looking at a fraction is take a whole. So it could be a candy bar, it could be a dollar, it could be a pizza, whatever it is, right? Then what do I do?
Divide it into an equal number of parts.
Equal number of parts, and how do I know how many parts I should divide it in?
The denominator, the number
Yeah,
of the denominator.
the number in the bottom, right? So I take a whole, I cut it into the number of pieces that is indicated on the bottom. Then what do I do?
Then you determine, the numerator is, you're discussing a portion.
A portion of those number of pieces, right? Okay.
A portion, yes.
Which is crazy, because that's supposed to be what this thing represents. Okay, so let's look at a different example here. Let's kind of think through this example as we go. Can you give me a different one that is not 1 on the numerator and the bottom is not too big? So give me a relatively small denominator, not 2, and then a numerator that's not equal to 1. Okay, so a numerator of 2, and then how about the bottom? 2/5. That's a beautiful one. And who said they like pizza? Did anybody say we like pizza?
As long as there's pineapple.
Okay, great. So let's do this one. Let's visualize this one as a pizza. And let's think about each step individually. So if I want to do in stupid English, stupid English says that this should be equal to 2/5. Japanese is slightly better. Cut something into 5 pieces. Out of those 5 pieces, take 2 of them. That's slightly better. Still a little confusing, right? Okay, but let's slow it way down. What's the first thing that we do?
It's one whole.
Step 1. Take one whole unit. And in this case, we're thinking pizza. Okay, so we've got a whole pizza. Oh, God. And you should definitely call the pizza people and tell them not to allow their workers to drink on the job. That's that for sure. and kind of get mad that your pizza looks more like an egg. Okay, so now then what? What's step 2?
Divide your pizza into 5 equal slices.
Yeah, whole into, and in this case, we will definitely say 5 equal sized pieces. How did I know it was 5?
No.
Yeah, the number of things in the denominator. And this is where we're not quite sure if the person making the pizza has been drinking, but we suspect that they have, right? Just because their pizza pieces are like really not. So let us pretend for a moment that those were equal sized pieces, right? Yeah, they're not equal sized pieces, but we'll pretend for a moment that they are. Okay, so the reason that I made that number of pieces is because the number on the bottom told me to do that, right? This is the number in denom, is how a nerd would say that, right? Okay, and what is the third step when we're constructing this fraction?
Determine how many to give out in the first, like the numerator.
Yeah,
How many am I handing out right now?
count
Yeah. 2.
2 of them. And maybe we'll call them slices because they are both slices of the whole and slices of pizza. And the reason that I knew to count 2 of them was because that's exactly what my numerator tells me to do. So here's 1 and here's 2. That whole thing, if I looked at this all the way over to that, is a representation of the concept of 2/5. So this, the number of them and I count, this is the number in the numerator. So let us agree immediately that there's a lot going on here, right? Okay. So now that we have that principle, let's think about some general ideas that come immediately from this. So we're going to look back at our guiding light, which is what I like to call the where is my brain moment in this video. There it is. There's my brain. Okay. So let's think for a moment what A over A is, and let's do some examples. Okay. So maybe the easiest fraction I can think about is 1 over 1. Okay, so let's do this whole construction. What did the bottom represent? The bottom we call the denominator, the parts of the whole. So how many parts am I going to cut this whole into?
Well, you're not going to cut it because you're going to leave it whole.
Leave it, and then how many of those things am I going to take?
You take the whole, make one.
Yeah, so how many do I have? I have 1 whole. So the claim is if I have 1 over 1, that is indeed equal to the thing that I started with. Let's take another example. Let's do 2 over 2. And maybe I'm going to go back to chocolate because now literally I'm salivating. It's just chocolate's too good, right? So there's the whole. I take the entire unit, don't make a single cut, and I take the whole thing. Must be whole, right? Okay. What does 2 over 2 mean? Let's go ahead and construct the fraction. What do we do to construct the fraction?
Draw your whole.
Draw my whole chocolate bar, then cut it into
2.
twos.
The denominator tells you 2.
Yeah, and it's not only 2, it's 2 equally sized pieces, right?
Exactly.
Yeah. Okay, and then after I've taken the 2 equally sized pieces, what do I then do?
You take 2 of them.
Take 2 of them. So the question is, well, how much of the total do I have? The whole thing.
Yes.
Okay. Should we do something exotic? Whoa, I don't know if I can. I don't think I can cut chocolate into 100 pieces. And even if I did, I wouldn't be happy to eat one of them. So, but 4 is kind of nice, right? Okay, so let's go ahead and think about 4. What does it mean 4 over 4? Take the whole piece of chocolate, cut it into
4 equal pieces.
equal size pieces. So there's my 4 equal size pieces, and then count.
Then take
4 of them.
from
So
the
first,
numerator and take, so you're basically, again, taking the whole thing.
yeah, so I have the whole thing. Okay, so let's do this thing of extrapolating. Any guesses what that immediately means if I have any a over a? If the numerator is identical to the denominator, well, what does that immediately mean?
It equals 1
Equals 1.
if you have a positive number.
Yeah, this is where things get really interesting. I'm going to make a claim that a cannot be 0. I don't actually believe that claim yet today. In fact, I'm going to challenge it.
Okay, I've been waiting for this. You mentioned it a few weeks ago.
Yeah, oh yeah, for sure. Okay, so what I want to do is I want to study 2 cases. We're going to call this division by 0, and we'll call this the 2 cases. Okay, so what we'll first do is we'll study case 1 is going to be non-zero numerator, 0 denominator. And for a base case, what we'll do is we'll look at like 1 divided by 0. And we'll go ahead and call this value, whatever it is, we'll call it like x. Okay, so in case 1, we're going to study this concept of doing the division of a non-zero number by a 0 number. So one of the things that I might ask you immediately, what do you know about multiplication and division?
18 times by 0.
Yeah, you're a little fast for old Anderson.
Sorry.
No, you're like 3 steps ahead of your teacher, 4 steps ahead of the class. I'll keep singing Aladdin, don't worry. What do you know about how they're related to each other?
Inverse property.
Inverse. So what you're saying is these are inverses. And in particular, we're going to do this really interesting thing. Let's go ahead and look at what we call 10 divided by 2. What is 10 divided by 2? 5. Okay, so let's figure out why you said this is 5. And I actually want to introduce some language here. I'm going to call this a quotient.
Right.
And then you all said the thing on the bottom was called the denominator. And then you all said the thing on the top was called a numerator. Okay. So let's go ahead and think about this problem from the standpoint of multiplication. The reason that 10 divided by 2 was 5 is because what? 2 times
5 equals 0.
is
10.
10. Okay, so now I want you to use the words in red. So let's go ahead and say the quotient. Let's go, oh, sugar. Yeah, let's go ahead and say,
Should push it on.
oh, sorry, thank you so much, Molly. Don't give up on me. Someday I'm not going to suck.
You're fine.
And then we'll call this thing what we said the numerator. So you said that the numerator divided by the denominator is the quotient. Another way to say that is that the denominator times the is the numerator. And you kind of see, do you see the inverse property there? Division is over there, the quotient's over there, but I can bring the division over to the other side via a multiplication, right? So let's test that one more. So let's do a second example like that. Let's do a, maybe, I don't know. Oh yeah, say it. 9 over 3, that's a really nice one. Do you mind if I do 12 over 3? Okay, so use the words again. What do we call the thing on top?
Numerator.
Thing on the bottom is called
Denominator.
denom. Numerator over denominator. So what is 12 divided by 3? 4. What do we call the output? Quotient. So let's think about this for a moment. What is the corresponding multiplication problem that is represented by this division problem?
4 times 3 or 3 times 4.
Yeah. The numerator is equal to the denominator times the quotient. Okay, so let's go back to our original problem. So now that we have that in our minds, let's think back to our original problem, the case 1 of division by 0, right? So case 1 looks something like this. We had a non-zero on the top. We've got a 0 on the bottom. And in this case, we're just going to look at 1 divided by 0. And let's pretend for a moment that this had an actual value of x. We don't know what the value is, but let's pretend that this was legal. Okay. What is the corresponding? So let's go ahead and introduce notation. What did we call the thing on the bottom again? Denom. What did we call the thing on top, Abby? Numerator. Okay, so if this was legal, what is the immediate statement? How do I undo the division problem and turn it into a multiplication problem?
0, x times 0.
So the numerator must be equal to the denominator times the quotient. But this is what I was talking about. You were 3 steps ahead of me. What is 0 times x? What would you say about 1 equals 0? I might say, oh, hell no. This is not possible, especially not on Tuesdays, right? Okay, so that's not a possibility. And in fact, what we say is anytime we have a non-zero number divided by a zero number, what does that immediately imply by this property? Is it ever possible to have a non-zero number divided by 0 and then get something that makes sense? Because if it did make sense, that would tell me that I could multiply the denominator by the quotient and get something that's non-zero. But what do you know? 0 times any number must be 0. So not possible to divide a non-zero number by 0. So what does that mean? It means anytime I have something that is non-zero on the top and 0 on the bottom, what do I say about that? Not defined. Okay, but that was just case 1, right? Could you guess what case 2 is?
Let's see. 0 divided by something, but not 0.
We might say 0 divided by 0. Okay, so let's go ahead and think about this for a moment. If I have 0 divided by 0, and let's pretend for a moment that this number exists. So let's pretend for a moment that this number is like x. Okay, what did we call the output? That's called the quotient. This thing right here, that's called the denom. This thing on top is called the numerator. What does it immediately mean that to take 0 divided by 0 is equal to x?
1.
Let's go real slow. Numerator divided by denominator is quotient. What would that mean in terms of multiplication? Numerator would be equal to the denominator times the quotient. So now, let's choose an x to make this true. Okay, so can someone choose an x to make this true? Okay, so if one person says x equal 2. Any other solutions?
Real numbers. Say that.
Could be 3, could be 4, could be 0, could be 10. What do you notice? What's up, brother? Oh, thank you so much. Yep, you got it. We have an infinite number of choices. Oh. Congratulations. So in other words, this x is not well defined. We could define it. Molly could say it's 2. Rebecca could say it's 5. Sandra could say it's 30. Could be anything, right? Okay, so we have these two situations. If I divide a non-zero number by 0, what do we say? It's nonsense. It's numerical nonsense. You can't multiply. Another way to say that is you can't multiply 0 by something that's non-zero and get a non-zero, right? Okay, so if I have a non-zero on top and a 0 on the bottom, I'm screwed. If I have a 0 on top and a 0 on the bottom, formally speaking, I can do that division if I look at it as an inverse of multiplication. But the problem is, how many choices do I have for the answer to that problem? Infinite number. So let me ask you this. Does that increase confusion or decrease confusion if we're all trying to get the same answer?
It infinitely increases
Confusion, because we could both have a right answer and have completely different solutions. So we have a choice. We could either say anytime you have a non-zero on top and a 0 on the bottom, answer is undefined, and when you have a 0 on top and a 0 on the bottom, we can define it, but there's an infinite number of choices. Or we could make the rule. Could you guess what rule we might impose? Don't divide by 0. So division by 0, let's just agree by convention, not by act of God, certainly not by an act of Congress, because I don't even remember what those are like, right? So we're going to agree by convention. Let's agree. Division by 0 breaks math. Right? And one of my students really made me laugh years ago. I think it was a she. I don't remember if it was a he or she. They know that I was into hip hop. And they drew this boat. And they said, hey, if I have a 0 in my sail and a non-zero in my boat, I'm okay. But if I have a non-zero in my sail, or any number in my sail, and a 0 in my boat, what happens?
You have a hole in your boat.
I have a hole in my boat. So this is no. Right?
That's really clever.
Yeah, and they said, this one I'm on. I can make this happen. I'm on here, right? Another one of my students had a different way to think about this. They sung this one. If I have a 0 on top and a non-zero on the bottom, I'm okay. But if I have any number on top and a 0 on the bottom, I'm KO'd. And they sung the little LL Cool J song. I'm gonna knock you out. Mama said knock you out, right? Okay, I know that song. That made me laugh.
I don't know what is KO.
KO is knockout. So like if a boxer,
Oh my goodness.
Okay.
Kato, somebody like.
so somebody that gets knocked out like falls over in the ring and the fight is over, right? And that's exactly what happens anytime I see a 0 in the bottom, right? I kind of get hit in the face, I fall over, and then, yep.
Wow. Nice.
Yeah. So what did we learn about that whole idea?
To make 0 a powerful number.
0 is a super powerful number.
0 is revolutionary.
It's revolutionary. Yeah, it is quite revolutionary.
Maybe the most important concept developed ever.
Yeah, and 1 is one I would put in there too.
Yeah,
Yeah.
0 is just like.
0 is really important for addition. 1 is really important for multiplication, right?
Yeah.
Yeah, so it depends. Yeah, that's right. Okay, so let's go back to the properties that we had here. What did we just claim? What did we just learn about here? Any fractions? Yeah, you got it. This whole thing is about fractions. Anytime we have a fraction where the numerator is equal to the denominator, that fraction's value is 1, except when the
The denominator is 0.
0. And what happens when a denominator of a fraction is equal to 0? It's undefined. Yeah, can't do it. Okay. No bueno. Yeah, I like that. Okay, so let's think about this now. What do you know about these two fractions? So if I multiply one fraction by another fraction, multiply across. And I want to do something that's kind of special. We're not going to study tons of cases of these, but I want to study at least one case. Let's do kind of a small situation. Let's do the one that you had. Let's do 1/2 times 2/5. We've seen both of these fractions before, right?
Yep.
Okay, so what I want to do is I want to think about multiplication, and we're going to think about a Snickers bar, thicker than a Snicker here. And then the question that I would ask you is, do you want to think of the one on the left as horizontal, or do you want to think the one on the left as vertical? Horizontal, okay. So we'll think about this one as horizontal. How do I, if I have a whole Snickers bar, what do I do to that Snickers bar here?
Cut it into two equal
Cut it into 2 equal pieces. And then what about this one?
Cut it into 5.
5 equal pieces. So 1, 2, 3, 4, 5. And then what we're going to think about is having like a line of Snickers bars, like a whole Snickers block. I'm already feeling hungry at this exact moment, because I'm literally just taking like a line of them, right? Okay. What does this tell me I'm going to do to all of those?
You're gonna cut it into.
I'm going to cut that entire thing into 2 pieces, right? What does this one tell me I'm going to do?
You're gonna cut it
5.
the other direction.
Yep.
In 5 equal pieces.
Well, what do you notice about the number of pieces I have left? 1, 2, 3, 4, 5, 6, 7, 8, 9.
10.
I have a total of 10 pieces. Then what we're going to do is, in this case, how many pieces do I have? So this one, 1/2. Out of the 1/2, how many of these 2 am I going to take? 1 of them. What about this one?
2.
2. So I take 1, 2 of these, and what we're going to think to ourselves is, which out of the new pieces, which of them are both highlighted? When we think about where do these things intersect? So if I have this one and these 2, where does that happen? Where are both of them highlighted in that new frame?
Top left.
Top left, right? Because I've got these 2 here, and then I've got this one coming down here. They intersect right there. Well, how many pieces are highlighted? 2. Well, check this out.
Bingo.
Ding, 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 ding. That's a way to visualize that. There's a little bit more going on there. We have to go back to really get it deep into this. We would have to go back into multiplication. But that's one way to visualize that property. Another way to say that is, when I have a fraction and I multiply by another fraction, what can I do? Multiply the things on top, multiply the things on bottom. And then, of course, lazy mathematicians literally say, like, I don't have to write the things explicitly.
You know what I mean.
Yeah, the bums. Okay. So what about this one? Division. Anybody remember something about division?
It's like I can do A divided by B, multiplied by D, divided by C, and this is the same as.
Yeah, so now that I have the multiplication, what can I
I can
do?
do A D divided by B times C, or AD divided by B times C.
Okay, and then this reminds me of one of my favorite Missy Elliott songs. Not my favorite, I think there's a better song that she sings, but it's pretty darn close. Anybody know the relationship, what we call those things? Yeah, we call that reciprocal. And another way to say that is flip it and reverse it.
So when you're dividing fractions, you do the inverse operation of it, which is the multiplication. And when you do that, you have to do the reciprocal of the last.
Of the right fraction. So if I have fraction, the left fraction divided by the right fraction, I leave the left fraction alone. I flip it and reverse it, and then I multiply. So when I flip it, the division turns into a multiplication, and then I go from there. Okay. And then I don't know if you all like platinum or gold more.
Platinum.
Yeah, okay. I've purchased a platinum ring for my wife, and I can tell you after purchasing that ring, I realized that platinum is more expensive than gold. So that made me laugh. We're going to call this the platinum standard. These two right here are what we're going to call the platinum standard of addition. If I add two fractions, so this is an addition of fraction sign, what do you see? So always, 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 I want us to be super conscious. When adding or subtracting fractions, there's some really special things that are happening. If I add two fractions with the same denominator, you know what we can do there? Add the numerators and leave the denominator alone. Once again, if I subtract two fractions with the same denominator, what can I do? Subtract the numerators and leave the denominator alone. Here's a claim I'm going to make. Don't ask me to choose only 5 tattoos that I would want in math. That's like asking me to choose my favorite type of chocolate, my favorite movie, my favorite song. There's too many good ones to choose from, right? But if you said, hey Jeff, for all the rational stuff that we're going to do, choose 5 formulas from which everything else comes, aka choose only 5 tattoos that you would need to master this entire lesson, these would be the 5. 1, 2, 3, 4, 5. If I know these things and I know how to factor, then I know everything in rational equations.
Are we allowed to talk about
Yeah.
the denominator is not equal? Or should I wait?
I want to get back to the question that you were asking earlier today.
Okay. Yeah.
What I might do actually is I might put that one. So if we look at this thing, you've got a really, really beautiful thing happening here. You're applying the right idea in a context that is not quite accurate, which is a great way to learn. Yeah. So I agree with you. So I want you to look right here. What operation is this?
Addition.
And the thing on the bottom?
Addition.
What operation is this? Multiplication. So you actually solved a problem. If this problem said this, if this problem said 2 times x times 4 over 3 times x times 6, I agree with you explicitly that you could actually break this into the following fraction, the exact way that you did. So if this multiplication, if this addition was instead a multiplication, the work that you did is absolutely gorgeous. But what operation is this? Addition. And what we'll notice is addition, sorry I'm writing on your work, does not behave well in division problems. And this one always confuses me. I should have a... Let me see if I can do this quickly. Okay, so let's think about this for a minute. What is 1 plus 2? 3. And what is 3 plus 2? 3 plus 2 is 5. So this fraction is actually 3 over 5. Another way to say 3 over 5 in decimal format is 0.6. But let's pretend for a moment that I could actually do what I've seen a lot of students do, which is just cancel these, right? Okay, so what would happen if I just canceled, or in your case, you did this thing, which is really kind of fun. I'm so glad you did it now, right? Because you're applying an idea that is accurate to a context that is not accurate. What if I could break those up? What is 2 divided by 2? 1. What is 1/3 plus 1? 4 over 3. Another way to say that is 1.3333. What do you notice about those two numbers? They're definitely not equal. The really, really cool thing about this is this mistake actually comes fundamentally from the right idea applied to a different context. So what the person making this mistake is trying to say is, hey Jeff, I know this rule that says if I have some operation on top and some operation on the bottom, I can do this thing where I break it into two different operations, and then one of the operation goes away, and I'm just left with the 1/3. So there's this other mistake that I see really often. Students will just literally like cancel these out and say like, oh, that fraction's 1/3. But what's the problem?
Addition.
This is addition. Addition does not behave well in division problems. We got to be super careful. However, if the problem has multiplication, then I'm set to go. So what was happening there?
So because the addition that was
You got to be careful, right? Yeah. We'll do one more example, and then we'll call this lecture for today. We'll stop the lecture. We've done some pretty good work. I'm not sure. Maybe we'll try number 8. So number 8 on page 5. The first thing I want to recognize before we start anything is, yeah, it's kind of fuzzy, huh? I'll try to rewrite it here for you. What type of problem is this if I think back to my 5 tattoos? A over B divided by C over...
Rational?
Yeah, we have a rational... Yep. What happens when I divide a fraction by another fraction? I call Missy Elliott up and I say, hey, what do I need to do? And she says, flip it and reverse it. Turn the division into a multiplication, take the right fraction, flip it over. So let's go ahead and think about this for a minute. I have x squared minus 2x minus 3. On the bottom I have something like x squared minus 4. Here I'm going to divide by 3 minus x over x plus 2. What's one of the first things I can do in that fraction? Flip the fraction on the right. So now I have x squared minus 2x minus 3 divided by x squared minus 4. flip the fraction on the right, what would that look like if I flipped it? Oh. Yeah, x plus 2 now goes on the top. And what's on the bottom?
3 minus x.
Okay. Question. Do I have the numerators connected by a sequence of multiplications?
Yes.
This one is for sure, but how about here?
Are you talking about the first numerator?
Yeah, these things right here.
No.
Yeah, they're not multiplications, they're the stupid subtractions, and addition and subtraction in division problems cause a big headache.
You need to factor.
Aha, you're telling me that I can transform these subtractions into multiplications by doing something called factoring. Okay, what would you do to factor those?
Do your, that nice little X diagram.
Yeah, we could do the AC method. Does anybody see immediately what those factors are going to be just by looking at that thing?
I see, but I do the X.
Yep.
Just to make sure.
One of them is going to be negative 3, another one is going to be positive 1. So here I have x plus 1 times x minus 3. For viewers at home, don't trust me. You don't know what I smoked this morning? Do not trust me. I don't know what the hell I'm talking about. Confirm it for yourself, then figure out whether or not I know what I'm doing, right? So here we'll go ahead and say that haven't changed anything. Here, I didn't smoke anything this morning. I refuse to screw up my lungs. You all don't know that sometimes I say stuff that it's just not funny. All right, what about this one?
It must be x plus 2 times x minus.
Yeah, so now all of a sudden we've got this thing called the difference of squares. We could do that via the AC method if we wanted to. All right. Now all of a sudden we've turned these ugly looking subtraction signs into a sequence of multiplication. What do you know if I have two separate fractions that I'm multiplying? What can I do if I have two separate fractions that I'm multiplying?
Marry those.
I can That is awesome. Molly says I can marry them. Yeah, that seems like the wedding night to me, huh? Sorry. You're not funny, Anderson. I need a crickets sound effect so that people can realize when a joke is just freaking.
Careful, you have an x plus n.
Where am I at?
Well, kind of on the top, on the numerator, initially it says x plus n.
Oh, sorry about that. Should be plus 1, right? Okay. Question. What do you know about the order of multiplication? Yeah, does it matter which order I do it in? So in particular, are there any of these things that look identical in the numerator and in the denominator?
X plus 2.
Okay, so for sure I have this thing x plus 2 over x plus 2. Any else? Any of the other ones look kind of nice, useful?
X minus 3 and 3 minus x.
Anything else? Well, these ones don't look like they're quite easy, right? I'm running out of room. What does a professional mathematician do when she runs out of room? Yep. Okay, so now I've got these fractions. They're all kind of squished up. What can I do with fractions when they're squished together? So if I have a times b over c times d, what can I do there? Break them apart. And the really nice thing about that is when I break these apart, x minus 3 over 3 minus x, x plus 1 over x minus 2. What do I immediately know about that fraction? That thing is 1. What do I immediately know about that fraction? Can I do anything to simplify it? This last one there. This thing right here, is there anything I can factor out of the top and the bottom to simplify it? Nah, the factor on top doesn't look at the factor on the bottom, no simplification. This one right there is kind of brutal, isn't it? It almost looks like I should be able to do what?
Just call it 1.
Just call it
We're in a
1.
big hurry.
Yeah, but the problem there though is that if we look at 3 minus x, so let's imagine for a minute, you just made a conjecture, Molly, which is just so gorgeous. So let's imagine that x is equal to 0. So everywhere I see an x, what am I going to put in? 0. So this is 0 minus 3. This thing is 3 minus 0. What is 0 minus 3?
Minus 3.
Minus 3. What is 3 minus 0? 3. What is negative 3 divided by 3? Yeah. Which is definitely not equal to 1. So even though it looks like this thing should be 1, we've just confirmed for at least one value of x that is definitely not equal to 1. In fact, it's equal to negative 1. And in fact, we have something even more powerful. Let's write this as 3 plus negative x. Now I want you to start getting mad at me, okay? You can get hangry. I'm feeling a little hangry at this exact moment, especially because we were talking about all that chocolate and cutting pieces up and sharing it. What did I just do there? What is negative 1 times negative 3? What is negative 1 times x? So literally, I just rewrote that line with a factor of negative 1 in it, right?
Yeah.
Okay. What do you notice here? What do both terms in the addition share?
Negative 1.
If both terms share a negative 1, what can I do with it?
Add it. Okay, you're pulling it.
Yeah, factor it, right?
Factor.
What do you know about addition? Does it matter what order you multiply by?
No, you can take that x and make it x.
And then what's x plus a negative 3?
Yes?
It's x minus 3, right?
Yes.
So everywhere I see a 3 minus x, I could write that as negative 1 times x minus 3. So everywhere I see a 3 minus x, we've just learned that I could write that as negative 1 times x minus 3. On the top I have x minus 3. Would you agree that anytime I have a number I can always multiply by 1?
Yes.
Okay. What do you know about x minus 3 divided by x minus 3? What? Yeah. That thing goes to 1. What is 1 divided by negative 1?
Negative 1.
Yeah. So now this is 1 times negative 1 times x plus 1 divided by x minus 2. And now I want you to slap me across the face relatively hard because I've run out of room and now I'm like doing the stupid thing where I like go to the side.
Don't be a rookie.
Don't be, you're so kind to me, Molly. So,
Get more paper.
yeah, Mom, you hear that? She's calling me out. Don't be a rookie. You didn't even slap me across the face and I listened to you. That's awesome. I can listen. I
Even
know.
though it's lunchtime.
Yeah, negative 1 times negative 1?
Negative 1.
Negative 1. And guess what we've just done?
Solve that darn thing.
We've simplified it
Yes.
for sure. The whole thing is complicated, so I don't know why they use the word simplify. That's a stupid word to me.
Relatively.
But there's nothing else I can do there, right? There's no more that I can pull out.
So it's a negative.
Yeah, and the negative comes from the fact that these two factors, the factor on the top and the factor on the bottom, are different by a negative scalar. So it's not that fraction, this fraction right here is not 1, this fraction is -1. And that is generally true. If you ever see a fraction where the top has a negative factor of the bottom, but they're both identical, that fraction has -1. And you can follow those steps that we did. Axel, I'm going to come see you in. Yeah.
So it doesn't matter if we do it that one way, if we inputted the 0, or
No, you can use either of those methods. Yeah, for sure. At this in 48B, something like that, when you get to this in the 48 sequence, it will matter, right? But for now, to get your head around it, the fact that you're recognizing that they're not identical is a really good start to that problem.
okay.
Yep. Should we call it a... Yep. And then I'll let you all practice the rest of that. All right, I'll see you in the next one. This is crazy fractions. My God. State of California.